I've already briefly described the program. I wish you would tell them your perspective on the program. They will introduce themselves as they get ready to ask questions.
Okay.
Introduce yourselves. I told them about the limitations that 8 of your team members are not here to participate.
Should we talk about the program at the end after we present? Or?
It's your choice.
We have some slides dedicated to the program.
That's, if we have time for that, that's a great way to organize it.
Okay.
Part of this. One of them, Sean. You have the floor. Go ahead.
You guys want to introduce yourselves first?
No, he said afterwards.
Oh, okay, sorry. Well, good afternoon, everybody. Welcome to the Team AirHeart's final presentation. We're a team of one of the teams of 4 teams sponsored by the Boeing Aerospace Capstone Project. The teams consisted of students from 5 different universities and faculty and coaches from Boeing as well. To get started, I'll start off with, my name is Micah Nugent, and I was the chief engineer for the team AirHeart. And I'll start off by talking about our team management. The team consisted of 11 students from 4 different universities, 3 from Purdue, 3 from BYU, 3 from Embry-Riddle, and 2 from Tuskegee. Our faculty advisors was Professor John Sullivan from Purdue, and his assistant, Eli Cohen, also from Purdue. And then our Boeing coaches was Kenny Foster and Vish from Boeing. His name is really hard to pronounce, so we like to be called Vish. A little bit of our management summary. We had 2 overseers of the project, the team leader and the chief engineer, the technical lead. And then below them were 6 IPTs that consisted of the different factors of the project. Each IPT had their leader, had a leader that went along with that IPT. And each member of the team was a part of at least 2 different IPTs to kind of spread the workload around evenly, give people more exposure to other areas. We also had a secretary for admin stuff and bookkeeping. That was for the first semester. For the second semester, we kind of switched to a more manufacturing-oriented structure. We still had the team leader and the chief engineer. However, each school had their own manufacturing lead. So this gave more leadership opportunities to students that otherwise would not be able to have a leadership role. And then also just made it a lot easier to coordinate. Each of the IPTs that's explained before, though, that system was still in place, but it was just an addition to the system. Our mission motivation, one of the strongest things we were going for in choosing a mission was impacting as many people as possible. And as a part of that, we found a necessity for an AED defibrillator type of system to get to people who are suffering from sudden cardiac arrest. So each year, approximately 424,000 people will suffer from sudden cardiac arrest. And among those people, only about 10% will be able to go on and live normal functioning lives. So if we were able to deliver an AED device or defibrillator device to these people within 5 to 6 minutes, we would be able to save approximately 160,000 lives per year, which to us had the biggest impact that we could possibly come up with. It would really make a huge impact on society. Over here on the right is a Google Maps overlay of what a traditional responder vehicle would have to take. This in blue would have to do this kind of Z-shaped route to get to where the victim was here at Starbucks. It would take them approximately 6 minutes to get there. And then the red line here is what our path for our youth may be able to take. And it would cut down time to about 2 minutes, dramatically increasing that person's chances of survival and normal life. We have some quotes here from first responders. We got a lot of positive feedback from first responders throughout the project. We really wanted to go to them and figure out, are we doing this correctly? Is this what you want? Just to get some positive feedback from them, or even negative feedback from them, and see what they wanted in a system that could deliver this device. I'll go into the design of the project. We considered many different types of systems, delivery systems in our conceptual design process. We had tilt rotors, tail setters, VTOL design, delta wings, flying wings, traditional conventional aircraft, and blended wing body. Here are some DSP sketches of the different concepts that we came up with. But ultimately, after discussing and basically a lot of hardship and trying to figure out what we wanted to go with, we ended up going with a blended wing body for a few reasons. Number one, we can get blended wing bodies to go very fast. We had that really high top speed design. In order to do that, we had to minimize drag and had to make a high propulsion system to keep that top speed up. It also has fairly good endurance and efficiency. And then also the payload capabilities or capacity. Our payload was basically an AED device, was about this big, and it was round. So fitting in, it was very conducive to a blended wing body design. We could really design the aircraft around that payload, the payload requirements. We had a lot of competing constraints when we came up with the product, when we came up with the mission. Boeing had a hand launch requirement. They wanted the aircraft to be hand launchable. We had a very high speed requirement. We wanted to cruise at 100 miles per hour. Because of this, these two regimes really fought, and it was very difficult for us to achieve both at the same time. So what we had to do is we had to design for a very high wing loading at our hand launch conditions. Because we designed for such a high wing loading, it was very difficult to achieve that wing loading. Over here on the right is a plot of our wing loading at hand launch, which is 130 units per meter squared. That's approximately 2 or 3 times what a traditional aircraft of this class would have to endure doing a hand launch. So it was very difficult to achieve that. As you can see, our max speed, as we increased our max speed, the wing loading dropped dramatically. Some compromise we had to make. We had to have very high wing loading for our hand launch, and we had to design a very high thrust weight ratio system, propulsion system. Going into our predicted aerodynamics, we iterated through several different types of airfoils for both the body and the wings. There were different airfoils. For the body, we finally chose a MACA 1117, mainly because it had adequate thickness to house the payload and all the internal structures and sensors that was in it. It also had a fairly aggressive stall regime at a pretty high angle of attack. For the wings, we chose an MH45, mainly because it had a significant amount of recurve at the trailing edge of the wings, which gave us better pitch stability. And it also has an aggressive angle of attack for the Reynolds numbers that we'd be flying at. We'd be flying at fairly high Reynolds numbers that we want to pre-class. Continuing on with aerodynamics, on the left we have a CL versus CD plot. One thing of note is that at our cruise condition, denoted it at the blue dot here and on this one here, that's our cruise condition. Our L over D max was not at our cruise condition, which kind of brought down the efficiency of what you would see in the traditional aircraft. However, we do have one of the lowest drags at our cruise condition, so that really allowed us to increase our top speed as much as possible. And then over here on the right, we have a CM versus alpha plot. With the blue dot, very high speed aircraft, we want to make sure that we can land at reasonable speeds. So after iterating a few times, we came up with a velocity of 37 miles per hour. At this condition, we would need a CL to trim of 0.76. We also wanted to keep our angle of attack less than 10 degrees to avoid stalling the aircraft with control surfaces. So after doing an analysis using AVL, we found an actual CL at this condition of 0.55. To trim, we would need an L1 deflection upward or negative 6.23 degrees. And this would give us a vertical descent velocity or impact velocity. We would hit the ground at around 2 miles per hour, which is much, much less than what we actually designed the structure and the payload to impact. So it was about 10 times less than what we were actually allowed. The landing results basically show that landing is possible, but we're going to be landing pretty fast. For the propulsion system, we wanted to design a very high-powered propulsion system to get that thrust to weight ratio up as high as we could. We chose a Turnigy Hell Drive competition series. It was an 800 kV motor, and the max power was 3,700 watts, which is very, very high for this class of aircraft. And the efficiency at cruise was 92% of this motor. The battery was a 10-cell battery. It delivered the maximum wattage that the motor could take. The maximum voltage that the motor could take. And then we got an ESC that was rated for 120 amps, even though the motor could only get a continuous 100 amps. We wanted to avoid any overheating of the system or the propulsion system, so that's why we kind of emphasized that. And the propeller was a 9x9 APC Spark. We wanted a very aggressive propeller so that we could have the widest range before we hit that windmill effect of the propeller. Basically, the windmill effect is when your prop is basically a windmill because you're not producing enough thrust. So we used Java prop to predict the performance of our propeller. And over here on the right is graphs of the efficiency and the thrust of our system, and the black circles are cruise condition. So you can see from the efficiency plot that the circle is at the highest efficiency possible for the propeller. That allowed us to really maximize our efficiency at cruise. And then we also had more than enough thrust at all of our flight regimes to achieve the mission. With this data, so our total efficiency of the entire propulsion system, the propeller and the motor, came out to be 53.1%, which is a very good power conversion for this type of system in this class of system. We also did some wind tunnel dynamic testing of the propeller inside the wind tunnel here at Embry-Riddle at 5,500 feet above sea level. The results of that were very, very promising. We had better results than what Java predicted, giving us more power than what we actually thought we were going to have. And we had much more power than what we needed for minimum requirement for our mission requirement. We had a thrust to weight ratio of 1.2 at our static thrust condition, and we had available thrust of 35.6% more than what we needed at our cruise, allowing us to accelerate above 100 miles per hour if we needed to. And then over here on the right is the actual data of thrust versus velocity for the 9x9 propeller, with the blue dot indicating our cruise condition. So it was about 19 newtons, 19.5 newtons of thrust at our cruise condition, when we really only needed 12.6 newtons to overcome drag. Now I'll hand off the presentation to Michelle.
I'm sorry if I sneeze. Allergy season is kind of a little rough on me this year. So here we have the 3D drawing. I know it's kind of hard to see. If there's any questions about extra details at the end in the appendices, we have each of the views in greater detail. One of the things I just wanted to point out here, though, is some of the major dimensions, the overall, so like the length and the size of the wingspan and the length of the total aircraft. So our wingspan is just over 50 inches. It's a little greater than 4 feet, which it's not too big. But we had a requirement for sizes had to be modular to carry around. So what we did is we made the wings detachable, which I'll go into further detail in a few slides. And so the length of the total aircraft is just over 24 inches, so a little more than 2 feet. This is a fairly small aircraft. We wanted to keep it as small as possible. That way the first responders, if they needed to take it out into the field with them for anything, whether it's to deliver first aid supplies to anybody that's outside of range that needed it quickly, things like that. And one of the things we focused on is if it doesn't need to be modular, if it's being sent from like a home base, it can just be kept put together as one whole aircraft and just sent out when it needs to be. It's faster that way, so for like the AED, if they needed to send it out from somewhere, especially like out in rural areas, it's just ready to go in no time. So for our preliminary structural design, we decided to use carbon fiber ribs for the body itself. One of the main reasons we went with carbon fiber is their strength to weight ratio. Our system, especially with our propulsion system, is very heavy, and we have to carry a 2.5-pound payload or up to a 2.5-pound payload. So we wanted to make sure everywhere else that we cut as much weight as possible. After all, this thing had to be hand launchable, and that was one of the hardest constraints that we had to make. So with the carbon fiber ribs, we cut that weight down as much as possible, and it was also easy to manufacture. Like Cameron will explain later on, BYU has a shop where it was easy. We could just submit the CAD files, and it was fairly cheap to get them. So this is just a little bit more detail of how our wing connection works. The rib right here is actually the outside of the body. What happens is the spars stick out of the wings, and the spars themselves go into the body through these ribs and connect inside of the payload compartment. And we decided to do that for 2 reasons. One, it goes through all 3 of the ribs as well as the compartment. It gives it a lot of rigidity for the wings. And we know that landing at such high speeds, if we land slightly off, hitting the wings and things like that, we need these things to be strong. So we decided to do that, and then the second reason is because this payload compartment right here also has to be held into the body. So we thought, okay, if we're in a hurry, if the first responders are in a hurry, they need to put this together real fast. And if it's not already together, 4 screws puts the entire thing together, wings, compartment, and everything. So we kind of combine together to work out as far as time and for the strength of the overall wing connection of the aircraft. So here's where we did some testing on the carbon fiber arrows. From calculations, we knew that our wings had to withstand an approximate 75 inch-pound moment. So what we did is we put the arrow in the device up here, as you can see, and then we weighted it down here. What ended up happening was we were fairly surprised. We had never had an experience with this kind of thing. We were expecting, a Dragon plate who comes with all these specs and things like that. We had no experience with the whole archery equipment. So when we put it in, we were pleasantly surprised that it did not fail until a moment of about 130 inch-pounds. So it gave us the confidence that we needed that this would stand up to the load that it would see during flight, and especially during landing. We also did an FEA analysis. We just wanted to see how the distribution was on the wings. And we used the 75-inch pounds like I mentioned before with that spark connection. And the result of this, we wanted to see kind of what our factor of safety was, how close we were, and things like that. So it gave us a factor of safety of 2.5, which is more than enough to send us forward with this design. We were fully confident that this would work. So this is one of the iterations of our design. Before, when we first did our very first model manufacturing, we realized that the body was not as solid as we could have hoped for. There was a lot of play in it. So what we decided was to implement this rib that goes across the body transverse. And what it did is it really strengthened that body side to side, whereas before it had a lot of play in it, and this really helped stiffen it up. So one of the consequences was this is, what I showed before, the payload. What happened was the compartment that held the payload as well as the battery right behind it. So there was a wall between the payload and battery, but now with this rib in here, as you can also see it here, that battery, that would get in the way of where we wanted our battery to go. So what ended up happening is we cut that payload compartment right behind, so the battery is now separate from the payload, and it actually ended up working out for us in the fact that we realized upon some of our first test flights that our CG was not quite in the right place. So that allowed us to move our battery, which is really quite heavy because it's a 10 cell, and it gave us the ability to move our CG around as we needed. So one of the other changes that we decided to make when we started manufacturing, we realized, holy cow, we have a ton of pieces. This is a very intricate aircraft to assemble, and we realized that it was like a puzzle. It was very difficult, things had to be marked out, planned strategically. It was a lot of interesting fun. So what we did is, this is our original design. We're similar to the way that the ribs, the body has ribs. We had ribs in the wings. But what we decided to do is, after flight testing, we realized that those wings had no give in their structure. So we thought, okay, do we really need the ribs in the wings? So what we did is we actually, with the Kevlar, the foam, and these carbon fiber spars, we realized that it was just unnecessary. It was over-designed, and it made manufacturing just way too time-consuming. So what we did is we took out all the ribs and the wings. It made putting the wings together no problem at all. It cut at least half the time out for that. Another change that we made was the way that the spar connects to the body. We realized these ribs on the outside of the body here weren't doing as much for our design as we could have hoped. And then the main purpose that they served was the wing connection. So what we did instead was we printed a mount that goes to like the main body ribs right here. And this is 3D printed. And we realized if the wings disconnect, this is likely going to be our failure. And that's great, because we can reprint one of these in a few hours and get it on in no time. It could be fixed in a day. So it gives a lot more rigidity to this connection, whereas before the wings had a little bit of play connection to the body. And that helped solve that problem. And then we did something similar to the motor mount. Whereas crash after crash after crash, we realized that our motor mount was seeing cracks due to stress, and it was just slowly breaking apart over and over. So even though our motor mount before was easy to manufacture, it was just a simple e-glass layout, we didn't want to make 20 different motor mounts while we figured out how to get this thing to fly. So what we did was a more robust motor mount that we 3D printed similar to how we did the wing connection, and that made it a lot more durable. And if it did break, it didn't take a day or two to lay it up and let it cure. All it did is we threw that CAD model back in our printer and got another one out in no time. So this is our payload accommodation. Like I mentioned before, we had to cut the back off, which was back here. So before there was a compartment on the back here that held the battery. We had to cut that off for that rib that went across the body to help give it more a rigid feel. We used a foam insert because this payload, when we got the payload, there's a company, and we mentioned at the end, I forget what it's called, they gave us an AED. It's a really small AED, really friendly to use, gives instructions. And what we realized is that AED is not as durable as we could hope for. So, when you come flying in at 40 miles an hour to try to land, next thing you know, the whole point of the mission is busted if we break that AED. So what we did is we did some testing, and we used this foam. It's called G-foam, which you can just get online. It's used for different purposes. And it helps cushion the payload when it's inside of the compartment to decrease that impact, that impulse on the payload itself. And here's just a kind of section cut to kind of show how everything fits together. And these are the holes that I mentioned before where the spar is attached into the payload compartment. Okay, so I'll talk a little bit about our subsystems. We use a Pixhawk autopilot, and the main reason was it was fairly cheap, and we had a guy up at BYU who's had quite a bit of experience. We haven't really used autopilot systems as much, so whatever he was comfortable with, we were comfortable with, and that's why we went with it. We also have a first-person view camera. We decided, if we're flying a 5-mile mission, and for some reason our autopilot isn't working, that pilot needs to be able to see what the heck is going on, and they need to be able to see where they're going. And then we also use a telemetry system. There's not much to really say about that one. So this is our subsystem integration. This just shows how everything's kind of wired together. It's a little bit of a mess. It's kind of all over the place here. But it just shows how everything hooks up to the battery, the ESC, and where our servos are. I'll show a little bit more on this one. This is where in the body everything sits. So as you can see, we have So we have the camera up front here with the motor. It gives the best field of vision if that pilot has to take over from the autopilot. And we have our servos here inside of the body, and then some of our autopilot GPS systems in the back there. And then of course we have the PO-STAT tube on the left. So now I'm going to hand it over to Cameron, who's going to go into more detail of our manufacturing.
So first of all, can anyone hear me in the back? All right, that's good. I'm Cameron Watanabe. I'll be finishing up with manufacturing. So a little bit about the manufacturing process. We started out with a table or a chart to find out the capabilities at each university. Now, the capabilities include the manufacturing and the rapid prototype and the quickness to get these parts out. So we decided at Purdue University, the main body and the final assembly were to be completed over there. At BYU, the internal structure and subsystems were to be completed. Subsystems meaning sensors. At ERAU, the wings and propulsion systems were to be finished there and assembled. Lastly, at Tuskegee University, the payload compartment and inspection tool. Internal structure of manufacture, which was done at BYU, as previously said. Basically, the ribs were cut from carbon fiber sheets created from a local vendor nearby. These were then CNC milled to give more accurate tolerances. And lastly, they were Dremel cut and gouted so these parts can be sent. As wing manufacturing goes, basically we were sent a foam mold and we were placed back into a glass slipper. Lastly, we inserted the ribs and spars to finish the process, which is shown here. Lessons learned that we got from it was a very time-intensive process. It was at least 1 week or a couple days that we had to actually finish this. Lastly, it was some epoxy buildup actually occurred on the leading edge of the wing. Payload compartment, this was done at Tuskegee University. What they did was they used a CNC wood mold shown on the left. They sprayed the mold and then vacuum bagged fiberglass to a finish. Lessons learned there, the arrangement of non-congruent piles, the wet layup onto the mold is very delicate because of the thickness of the fiberglass. The vacuum bag setup and care is labor intensive, just like the wings at ERAU. And lastly, orthogonal corners are susceptible to pinching and discontinuities. Body manufacturing was done at Purdue. The process was started as a CNC wood mold shown on the left. They applied a feather fill to coat the mold, applied a 2K clear coat for sealing, vacuum bagged Kevlar aromatic composites to finish. What they had learned was vacuum bag is prone to tears. Again, there's that epoxy buildup with the wings and manufacturing. However, it was very strong and durable to what we wanted. So upon testing, on flight testing, we discovered that the wings would actually rip and tear apart upon landing or hard landings. So how were we supposed to fix that? The way that we would do it is they were constructed to just fall upon impact. What it does is it decreases the time for repairability. It also prevented damage to the wing, in which we would simply foam core wrapped in a composite in fiberglass and carbon fiber. Likewise with the wingtips. The wings were also very difficult to manufacture. As said previously, it was done with ribs and foam used a glass slipper. However, the ribs, they were really complicated, therefore we just got rid of it, simplifying the manufacturing process and still retain the sufficient strength needed. Internally, as said by Michelle in the 3D CAD model, the fuselage of the body was prone to twisting and just like bending. So a 3D printed spar was created in order to get rid of that, plus along with the wing mounts and the motor mount. The result, it actually increased our durability and integrity of, or the rigidity of our fuselage connected to the wings. And it was a very modular design. So as a final result, after completing the winglet design, the fuselage design, it was very rigid, as shown here at the fly. So lastly, performance. For flight testing, this is just a compilation of all flight testing, which was done at BWU, Embry-Riddle, and Purdue University.
There's a little bit of theatrics to the video because it was meant for a different audience, but I think you guys will enjoy it. That's it. But as you can see, the body and the entire aircraft had to withstand very, very rough and time after time impacts, landing crashes. The body was amazingly rigid and durable.
Okay, so needless to say, we know how to crash an airplane now.
Yeah. So this day, it was gusting about 25 miles per hour with a constant wind of about 20 miles per hour. So that's why it's going like this a lot. It was really hard to control. This was the day before we presented to Boeing, so we really wanted to have at least one successful flight.
So bottom line from this project, building an aircraft is not easy. So in comparison with our intended what we wanted to have to what we actually had was we had an unstable aircraft due to software discrepancies. Control surfaces were initially inadequate, where we had a half-span control surface rather than a full-span control surface. We were not expecting our aircraft to survive that long, but structurally and overall the skin, it provided much more rigidity than we expected. So, as previously said, ABL predicted a CG close to 0.31 meters, which is correlated to about a foot from the nose. So where our actual CG was closer to 0.22 meters, which is about 8 inches from our nose. Improvements made were the 3D printed parts as shown in previous slides, the motor mount, the wing structure. We also added a tail as shown in the previous video to increase pitch control at lower speeds. Budget-wise, we intended to have our projected costs at least $3,000, with $5,000 remaining. However, in our final cost, we ended up with about $4,000. We ended up using about $4,000 with $4,000 in remaining, which was all done to shipping. Lessons learned from this project: it's very difficult to work in different time zones, especially at Tuskegee, Purdue, and BYU, all at different time zones. Again, hard to predict aircraft. Communication is key, especially with scheduling and meeting. preparing ahead of time. We needed to manufacture early. We set everything up early, and we allowed slip for it. However, that didn't happen. Major benefits. We experienced working. We enjoyed working with people around with the other universities. We like that. We also had some networking with them, and we had a deeper understanding of our knowledge of mechanics of flight. Lastly, software experience. We had very little during school-wise. However, with this project, we learned exceptionally more. And of course, the driver factor, which we all love. Special contributions, Roger Nilsson, which gave us the AED, which Michelle had presented, CAD model, the full model as well, and Brock Zoble at Golden Tip Arrows for giving us the arrows used for our wing spars. That concludes our presentation. I will open up the floor for questions.
Sorry, Kristen, I know we went over.
Yeah, that's
But, you know, it's a big fun.
It's difficult, but we pulled through it.
So I guess we'll introduce ourselves again. I'm Daniel Caraway. I'm with Boeing. I'm in St. Louis, Defense. I'm Eli Jones. I'm a flight test engineer at AirHeart.
I'm at Brad, Lockheed Martin Stunt Works, and they're all in simulation.
Nice for you guys to be here.
Yes, thank you.
Start this time out, or you
I can start. Great job. Yes, it's difficult to build an airplane. Sometimes the goal is to crash the airplane, and that way, when you fail, it actually works. And something we can learn from that one. And what you chose to do, a flying wing, even makes the issue even harder, because CG becomes so phenomenally critical, understanding all the pitching moments. So you took on a very hard task. Had you gotten to flight, had you gotten 150 knots, you would have found that there were other barriers that stood in your way in things that your professors haven't told you about, like aeronautics. The thing, I can show you some big videos of blowing apart. So, but you didn't have to deal with that. Flying wings notorious for pitch break. Sure you are aware of that. So the tail, great solution for it. And then I'd say the only thing that was kind of confusing through the whole presentation is there weren't consistent units.
Okay, I understand.
Yeah.
So what ended up happening with this is, as expected, like we've always been taught throughout our 4 years here at school, is use English units, because that's what most of the industry uses. So what happened was we did all of this analysis in English units. We did all the, as you can see, all the NX models, which I spent a ton of time, were all in inches and feet. All of this in English units. And then our coach comes to us one day and says, we want you to start working in metric. We're like, okay, but why? And apparently because our coach is very used to the metric system. He does a lot of work with like electric motorcycles and electric cars. Apparently when he does his stuff, he does it in metric. So he said, from now on, I do everything in metric. So there was not time to go back and do all the analysis of different unit systems, which is unfortunate because I can understand why it's very confusing. It was confusing for us at times, because every time we would tell each other, this is what I got as a result, you made sure that we knew, okay, I did, you know, Dr. Sullivan wanted us to do this in metric. Well, this was already done in English. And it was interesting.
And the one that really struck with me was you had a comment about landing December at 2 miles per hour. And I just can't think that way. You know, to me, it's feet per second, feet per minute. You know, what that will But yeah, I think it's a great job. But I think that the mission that they chose is a great one. Being able to get a first responder equipment to a location, even if it's just aspirin.
Yeah.
Correct. You know, that's one thing to do.
Originally, we wanted to tackle the control system. That was our idea. You know, landing at high speed is not ideal, especially with people around.
Get a heart attack or something.
Well, hey, he's there. So we were originally going to do a VTOL system, and we realized time constraint-wise that it just probably wasn't going to happen.
Yeah.
So we went with the traditional landing system. then if we had time, which we did not, we were gonna try to implement that. Because with FAA regulations, it had to only be used in rural, our mission was for rural environments, simply because of the way the regulations are right now. So I mean, I know some of the companies like Amazon, and then they're just now starting using the quadcopters and things like that, but they don't travel at 100 miles per hour, so maybe someday we'll see something along that line.
Good job.
Yeah, I agree. Really interesting concept. For maybe or other medical like it's very needed. But the approach at 40 miles an hour is
Yeah.
also somewhat amusing. Yeah, you guys did a really good job. Big challenge taking on a flying wing design. And I'm sure as you guys discovered, it's great for speed. It's great for realizing some efficiencies, but it's
Yeah.
also really challenging stability.
Which is one of the things we weren't fully aware of when we first chose this design, that became painstakingly aware as we continued to
Sure.
go on. So.
Sure. So yeah, when you cut off that conventional tail,
We actually made that tail the day before the fly out, because we didn't have any successful flights. We were like, well, all right, I'm pretty sure our tail will fix this problem. It'll give us the pitch stability we needed, and it worked perfectly the way it was supposed to do.
yeah. One question I had as you were sort of iterating design is, did you ever consider twisting the wing?
We actually did an extensive, probably 2-week analysis of wing twist. We did analysis from -1 to -4 degrees of twist downward, and it helped the system. It helped in the pitch stability. We were doing that with a different wing, airfoil. So we originally had a NACA 5 series with no recurve or reflex on the trailing edge, which we found to be very problematic as far as the analysis goes. So we said, okay, we can either twist these wings, which is going to complicate manufacturing a ton, because to get a wing twist is very hard, very difficult to do, especially when you're inserting the sparks through there. It would be very complicated geometry. Or we could switch to a different airfoil with reflex on it or recurve. So we did an extensive analysis on the trade-offs and the benefits of it, and we ultimately ended up going with the Chinese 45, which still didn't have the adequate pitch control. One of the reasons that we know now that the pitch control was inadequate was the moment arm. From where the control surfaces lay to the CG was only like 2.5 inches. So we had this really small moment arm, even though we were creating a lot of forces on our control surfaces at those low speeds where there's not enough flow going over the control surfaces. We didn't have that pitch control. One thing that we could do instead of adding a tail is maybe move the wings back a little bit or sweep the wings more. Then you run into other problems like spanwise flow and other things.
So really creative using the arrows for the wings more. I thought that was great. In the decision to remove the
They care about the ribs.
yeah, the ribs.
Yeah.
In the decision to remove the ribs, did you do like a trade-off in whether or not it would be better to remove the foam instead of the ribs?
The thing with the ribs and the foam is that the foam is actually easier to cut. So if we needed to remake a wing, it was even faster than just cutting the ribs again. And we can cut the foam here not as accurately as at some other schools because they have the actual motorized hot wire cutters. We can do it manually. The trade-off was simply that it was a lot easier to cut foam than it is to cut a series of ribs, especially with the ribs being certain tolerances and the holes for the spars. The foam was just the easier way to go.
And we would still need to make a foam mold to make the glass slipper like it was before. We would just not use the foam. However, when you composite foam between two pieces of composite like e-glass that we use, the bending resistance, because you really increase that, that's moment of inertia, it really increases the bending resistance. So it was definitely adequate. It is so much simpler to just do that. So.
I guess my last question was just with regard to variability and the payload. Did you guys have any requirements for like different payload? Was just the AED that you were designing to, or?
So the mission itself was the RFP that Boeing gave us. It was very vague. It was kind of wide open. It didn't necessarily say that any aircraft had to carry the payload or had to do this mission or whatnot. It gave a list of suggestions of possible missions, search and rescue, things along that line. We took kind of a different path, I guess, from the other 3 teams. We kind of wanted to do something different, and that's how we came up with this. So as far as payload requirements, it was mostly, the constraints were simply the aircraft. It wasn't given to us by Boeing or anybody else.
We could swap out payloads, so we could put like a GPS device if somebody was stranded somewhere, we could find them plane and then drop it into GPS. We could also do anti-venom serum, first aid kits, water bottles, food, basically anything that could fit inside that payload compartment, which was relatively large. It was about this big and weighed under 2.5 pounds. It gives you a lot of play with what you actually want to put inside the aircraft.
Okay, yeah, well, I guess where I was going with that is, in your analysis for like the S&C, did you look at the CG migration to the chain payload?
Yes, we wanted to make sure, that's one of the reasons why it was really beneficial to be able to move that battery around, which was about 30% of the weight of the aircraft, and then we could also move a lot of internal components around. We can play with that. We can move that CG quite a bit if we needed to.
Yeah, one of the things that we discussed with the payload, or one of the main things we designed around was the AED, because it was the heaviest of any of the payloads that we could deliver. And what we did is we found a CG of that payload to help us simulate our manufacturing constraints. So we knew that if we could carry the payload, the AED successfully, could we do it without that? And if we could do both of those, then we could pretty much hit anything between.
Great job. So I'll definitely reiterate, great job on the project overall. Very tough challenge you guys had. I like you guys use your resources rather well, especially with the arrows and some of the other resources that you guys had. So great job on that. I think, especially with some of the teammates having kind of extracurricular interest in these arrows. Like, great to pull on these and find it actually very resourceful and help out a lot of ways that you never really think, never really thought.
Yeah, I don't think we would have thought of the air thing or otherwise.
So, first thing, I guess I'll talk about the propulsion system, or not, yeah, propulsion system is, let's see, the ESC. So you guys, I think I heard you say you undersized the ESC for the motor, correct?
We oversized it, so the motor was rated for 100 amp continuous draw, like 105 amp burst for 15 seconds, which was really never going to happen. We oversized it to be able to deliver 120 amps. This way, the ESC wouldn't overheat and everything.
Okay, yeah. Just be very careful with that because these ESCs will actually pull more amperage and can fail. And so I think it's good that you did oversize it because they end up pulling more in dynamic conditions. So.
Yeah, we wanted to avoid the ESC blowing up because those are prone to basically overheating and blowing up when they're overstressed.
And so I noticed too on your guys' electrical diagram, I think you didn't have a parallel power supply to the ESC to your flight control surface.
Like a secondary? I'm sorry.
Yeah,
Secondary power supply? Yeah, we weren't able to design in a secondary power supplies. So if the main battery failed, then we wouldn't have control surfaces or anything like that.
Right,
So, one thing that would be absolutely necessary if it was to be made commercially is there would definitely have to be some type of system to power those in case of a battery failure or some other.
Yeah. And then just a couple comments on some of the structures. I think slide 23 is where I got some notes written down. I really like the idea, I guess, with the wing and pulling that through multiple ribs of this state. I thought that was a good idea. And that'll help basically distribute your moment through that connection. So that was a very good idea that you had with the multiple ribs and the fuselage. And then with the changes that you guys made with adding in those 3D printed parts at the wing, I felt that was a pretty good job there. I was curious, do you know how much of a weight impact that had? Whereas those ribs were probably pretty light compared to the 3D printed material.
So in the rapid prototype printers, they actually used the low density plastic. It was a little heavier than the 3 ribs that it replaced, but not significant enough to really cause it.
Another thing is it decreased the complexity of manufacturing, putting together, and brought I don't know, you saw those nosedive crashes at 40 miles an hour. Instead of spending 5 hours or an entire day to fix those and cut it down to 1 hour, we could just throw it, slap in some more main connections, and it would just, everything goes. So the modularity that it provided, almost worth it. Is a very good trade-off to the design.
To know exactly where it would fail was really helpful. So even if our wings fell off, the wings weren't breaking. The wing tips, like he had mentioned, they would break, but they were pretty improvised, because we mess around with the size of those a lot, and found that we really needed to be worried about what we were going to design. So with that, the wing connection and the motor mount, they could break, and it was really easy to just put a new system in place.
And actually, overall, after all the design changes we made to the structure of the aircraft, it ended up lighter, about half a pound lighter than the original.
Yeah, we took out a lot of carbon fiber and stuff like that.
And the body, so the body was a little bit, but it was a Kevlar, and then AeroMat foam, and another piece of Kevlar. It was extremely, extremely strong. It didn't bend. A lot of times if you hit like that, it would bend in or concave in, and it didn't have any damage whatsoever, so some scratches. We were very, very happy with the capabilities of the body.
Our very first crash almost wrecked our motor entirely. So that was one of the reasons what prompted us to change how our motor mount was designed. So we almost completely just destroyed an entire motor. It was not one of the cheaper parts of the aircraft, so that's what prompted that mostly.